Here is the next example of MOSFET AC analysis. Basically, we know that it is NPN N-channel MOSFET. Okay, it's a N-channel MOSFET. Now it's the same example which we used in the previous case or previous example. The only difference is I connected a capacitor to the source. So while doing AC analysis, the source is going to be directly grounded, so I can use the Pi model. So while doing DC analysis, the process is same what I did in the previous case. So capacitor is going to act like open circuit. So in DC, so remove all the capacitors. So this is the rest of the circuit. Okay, we will assume the transistor is working in saturation mode. So that's the ID equation, found VGS, ID, explained everything clearly in the previous video. Please watch the previous video if you haven't. And we found that ID equal to 0.115 milliampere. Okay, until this is DC analysis. Now while doing AC analysis, I'm going to use the Pi model because my source is grounded while doing AC analysis. So here is the AC analysis Pi model. We are doing it Pi model because source is grounded while doing AC analysis. So we found from the DC analysis ID equal to 0.115 milliampere, and we also this is the equation for GM. We found that that's 0.428 millisiemen. Okay, and R0 is the resistance connected between the source and drain. That's VOD. Sometimes you will get lambda, which is 1 over VA. That's 869 kilo ohm. So that's a very big number. Now what is my input resistance? Rn is same as you will see, only 50k. That is my input resistance. What is my output resistance? R out, when I look from here just before the output connected, RD parallel with R0. So my output resistance here is 4k parallel with 869k. 869k parallel with 4k, very big number, and small number parallel. This value is approximately equal to 4k. It's going to be little less than 4k, but we can take it as 4k because the difference is huge. Now the gain is V0 over V input. Okay, so I'm going to write down equation for V0. So my V0 equal to, these two are in parallel, V0 equal to RD parallel with RL parallel with R0. Actually 3 of them are in parallel, times minus GM times VGS. Now what is VGS? VGS same as the V input. Input voltage and VGS are same. Vn equal to VGS. So I'm going to replace this VGS with Vn. So V0 over Vn equal to RD, which is 4k parallel with 869k parallel with R0. Sorry, RL is 4k. That's R0, by the way. So 4k parallel with 4k, which is 2k. 2k parallel with 869. Further, difference is too high, so it's approximately 2 kilo ohm times minus GM we just found, which is 0.46428. Okay, minus 0.428. So this is 2k times minus 0.428. Very this is in milli, this is in kilo, so that's going to be cancel out. It's approximately minus 0.856 volt per volt. That's with the load. Even without load, V0 over Vn, this is AV0 without load. So if I do not have load, this is going to be 4k times parallel with 869k. So we'll end up with 4k minus 0.428. You will end up with 1.4 712 volt per volt. This is also negative. That's AV naught. And GV overall gain is AV times Rn over Rn plus R sig. AV is minus 0.856. Input resistance is 50k and signal resistance is 20k. So that value is minus 0.611 volt per volt. The waveforms are going to be similar to the waveforms you draw in the previous video, or I draw in the previous video. Please go through them. I mean, I'm making these videos almost after 1 or 2 a.m. At this point it's 2:37 a.m. So I did it so fast. Please watch the previous video to get more knowledge. Okay, I'll stop my videos here. I hope these videos will be helpful for your test 3. Thank you guys.